Greetings and welcome back, to the video series on trend lines and regression analysis. In this particular video, we are going to look into residual analysis and regression assumptions. Recall that residuals are the observed errors, which are the differences between the actual value and the estimated values of the dependent variable using the regression equation. If we look at this graph here, it shows you the residual plot generated, where it is a scatter diagram of the residuals with the values of the independent variable on the x-axis. So in the home value data, this will be the square feet. The standard residual is the residuals divided by the standard deviation. Standard residual describe how far each residual is from its mean in units of standard deviations. It is useful in checking assumptions underlying regression analysis, which we will address shortly, and to detect outliers that may be causing bias to the results. The rule of thumb is that standard residuals outside ±2 or ±3 standard deviation are potential outliers. Checking for assumptions. Statistical hypothesis tests associated with regression analysis are predicted on some key assumptions about the data. First assumption is on the linearity. This is usually checked by examining a scatter diagram of the data or by examining the residual plot. If the model is appropriate, then the residual should appear to be randomly scattered about 0 with no proper apparent pattern. If the residual exhibits some defined pattern, then there is good evidence that some of the functional form might be a better fit to the data. Second assumption, normality of errors. Regression analysis assumes that the errors for each individual value of x are normally distributed, with a mean of 0. This can be verified by examining the histogram of standard residuals and inspecting for a bell-shaped distribution, or by using more formal goodness of fit tests. It is usually difficult to evaluate normality with small sample sizes. However, regression analysis is fairly robust against departures from normality. So in most cases, this is not a serious issue. Excuse me. The third assumption made is homoscedasticity, which is the variation about the regression line is constant for all values of independent variables. This can also be evaluated by examining the residual plot and looking for large differences in the variances at different values of the independent variable. The last assumption is independence of variables, where it is looking at the successive observations should not be related. If they appear to be correlated, for example, appearing to become larger over time or exhibiting a cyclical type of pattern, then this assumption is violated. Correlation among successive observations over time is called autocorrelation and can be identified by residual plots having clusters of residuals with the same sign. Therefore, when time is the independent variable, this assumption is very important. That successive observations should not be related. Let's look at an example, to check regression assumptions for the home market value data. Okay, when we look at the scatter diagram for the market value data, it appears to be linear. Okay, and when we look at the residual plot, there are no specific pattern that we can detect in this particular plot. Okay, normality of errors. This figure here shows a histogram of the standard residuals for the market value data. The distribution appears to be somewhat positively skewed, but does not appear to have a serious departure away from normality. Next, we look at homoscedasticity. Okay, in the residual plot here, it shows no serious difference in the spread of data for different values of x, particularly if the outlier is eliminated. Okay, and lastly, independence of errors. Okay, the home market value data is a cross-sectional data. So in this particular case, okay, we can assume that these assumptions will hold.